All right, so we were working in class here, and we were on page 15 of the notes. This is your 2D projectiles. And we were getting down to these maxima questions. At what angle should a projectile be fired to maximize? We started talking about it, but we didn't quite finish. Let's wrap that up right now. A student made a very wise comment that from horizontal projectiles, we learned that it was only the height of the cliff that determined the time of flight. So making that connection between height and time of flight over here, that's a pretty sensible option. Anyway, let's go figure this out. So at what angle should a projectile be fired to maximize? Height might actually be the easiest one of all to check out. In fact, Angry Birds teaches us that just fine. Let's go check this out. If we go to Angry Birds, there it is. Give you a little sound. Fantastic. Now, uh-oh. I know this thing's going to give me trouble, so I'm going to refresh it. Here we go. There's your little music. There we go. No critique on my playing quality, please. So the easiest thing to judge here, just from this video, is at what angle should you project it to maximize the height? Well, here you see this is a horizontal projectile. If I release it here, that's 0 degrees. But as you bring the bird down, we're approaching, that's about 45 degrees. And then we're approaching 90. Now, this game doesn't allow you actually to hit 90 at full strength, which tells you something as well. You want to maximize the height. Not only do you need to get the angle right, but you'll see here that the VI, or the strength of this slingshot, makes a difference too. So a common answer is something around 45 degrees will maximize the height, but let's try it out. Here's about a 45-degree launch at full VI, full strength. Thank you, Angry Bird. See how high he went. Went up to just this layer here. Know what you call that? From the mid blue to the dark blue. Maybe we call that our tropopause or something of that nature. Now, if we increase the angle now, we get this thing closer to 90. I want to keep it at full strength, so we can't quite hit 90. Watch what happens to the height. Woo! Oh, almost got the kill. Anyway, notice that's much higher. In fact, as your angle approaches 90 degrees, aka straight up, you will definitely maximize the height. Well, that piece that's related to it is a timepiece. We can approximate that here as well. So let me refresh this. Let's do our 45 again. Now, you could time this yourself, but let's go for our 45. Let's do a little timing here. We'll do a 1,000. Ready? 1,000, 1,000, 1,000, 4. About at 4 it hit. Come on back over here. If we increase that angle, get close to 90, let's try it again. 1,000, 1,000, 1,000, 1,000, 5. So we get more time with that greater angle as well. So bringing this back over here, the angle, we don't need Angry Birds singing to us. See Angry Birds? It appears that the max height occurs when the angle approaches straight up, so that's going to be 90 degrees. And that max time of flight seems to be at 90 degrees, but we can quantify that one a bit better. We watch this in class, but let me show it to you just the same. This is what they call the long home run. Let's shrink this down a little bit. Long home runs on YouTube there. So this guy's about to knock a ball real far, and you'll see it's quite a hit. The question is, how long does it take? So let's try to time it. We got our little stopwatch over here. I'm ready. Here it is. There's the ball, and stop. A little over 5 seconds I got on that one. Okay, good. Now, that's one of the longest home runs of 2019, midway through the video, so that's a heck of a hit. Took about 5:20 we saw over there, 5.2. Let's do it for a standard infield pop-up. So this is not any sort of record-breaking hit. Standard infield pop-up. The difference primarily here for our concern is that the previous hit was somewhere around a 35, 40, 45-degree angle. This one is going to be closer to a 90-degree angle. So let's get the time on this one. Oh, missed it. I made a mistake. There we go. Oh my goodness, what did I do? I don't want a timer. Pause for station identification. All right, we're back. So let's check this one out again. Let's get our timer ready to go. Start. Stop. So about 6.6 here, you're talking about a full second and a half greater on a standard infield pop-up. And that actually helps us confirm the time of flight goes with the height, maximized at 90 degrees. Thing to watch out for, of course, if the maxima are not among the choices. This is often a multiple choice question. Say what provides you the max time of flight, what provides you the max height. Pick the closest to 90. Simple subtraction. 85 degrees will give you more time of flight than 75. 63 degrees will give you a greater height, max height, than 61 degrees. The other one is the range. So range, people often say, oh, wait a minute, this thing should go the farthest when it is then aimed straight ahead. The problem with that is it will have no time of flight. It'll just be along the ground. So how do we get this thing to go far? Well, we need to send it forward, but we also need to send it up. Forward and up, because the up will provide you time to travel forward. So where does this maximize? Well, you kind of know this if you throw a ball or hit a baseball. You see this. And theoretically, at least, what you will find, let's go back to our Angry Birds. See, will they let us keep playing? Here we go. So if we watch here, we can shoot this at a few different angles. If we have like one of the steeper angles, let's say this is maybe like 65, 70 degrees. It lands over here a little bit past this setup. If we have this at a shallower angle, well, actually, let's go to something kind of in between, almost like a 45, right around here. Ooh, that one went farther. And then if we actually put more forward motion, something like this, that's going to hit the structure, but you can roughly identify where it would have landed. This is maybe like a 25, 30 degree angle. It hits here, but follow that, it would have landed somewhere around here. That one actually is pretty similar to the first one, the tall one. Okay, good. So in fact, hopefully you notice there, it's that mid angle, it's 45 degrees, that will maximize the range. We'll try something out in class to demonstrate this as well. By the way, at any angle, the faster you shoot it, the farther it will go, the higher it will go, the longer it will take. So that, of course, is the Angry Birds there. When you pull it back more versus less, obviously it's going to go farther, higher, etc. So I won't pull all the way back. I'll pull a little bit of the way back. Does not go as high, does not go as far, does not take as long. If I follow that same exact angle and go back farther, you will see the entire parabola stretches way out, farther, higher, longer. Okay, good. Good. Last bit. How can the range of an angled projectile be increased? So, of course, you can increase the VI. If you shoot it faster, you just saw that in Angry Birds, it will go farther. Range, of course, is dx. Actually, how can the time of flight be increased? You also can increase the VI. And this is unlike the horizontal projectile. This one actually will give you more height and more time of flight. All right, what's another way you can do it? Well, you can get theta, maximum range dx, get theta as close as you can to 45 degrees. To maximize the time of flight, you don't want to get theta to 45, you want to get theta as close as you can to 90 degrees. How about here? Well, there's a little sketch over here. If you shoot the same ball or Angry Bird from this location, you get a path kind of like this. If you instead elevate the launch height, so put your cannon up on a cliff, at first the path looks the same, but then the ball keeps on going. So you actually get both a greater range, it lands farther away, that's a greater dx, and also, of course, it takes more time. So lifting it up, be careful, it doesn't somehow cut it off. Don't imagine it cuts off the front. It's the same path, but then it increases the tail. So we can increase the launch height, aka launch, L-A-U-N-C-H, height. Sometimes what we also call our dy. And it's the same thing down below. Increase your launch height. There we go. And finally, these paths will all be increased if we go to the moon, which of course effectively means decrease the acceleration due to gravity, decrease that 9.81, so decrease little g. All right, this is the same. That will give you farther, more range, and that will also give you more time. The parabola in that situation would look something like this. Okay, something you could look that up actually. Home runs hit on the moon, how would it look? A towering home run, how far would it go? All right, so that's the stuff you need to really wrap up W48. Hopefully the slow treatment didn't break you, but this will get you through those questions. Adios.